Section 4.2 is all about classifying chemical reactions, and there's three types of chemical reactions that we'll learn to recognize. Firstly, we'll learn about precipitation reactions. And this takes a little bit of time because we have to learn about some solubility rules, and that's a bit of a memorization task. But we'll try and take it slowly, and hopefully it's not too challenging for you. To understand precipitation reactions, we first need to think about what happens when an ionic compound dissolves in water. And it's quite interesting. What happens is that the water molecules interact with the ions on the surface of our crystal, and they pluck those ions off one at a time, producing a solution that is composed of individual cations and anions that are able to move around independently of each other. So effectively what happens is that the attractive forces between water molecules and the ions overcome the forces between the oppositely charged ions holding the crystal together, and the ionic compound dissolves, producing cations and anions that are in solution. So how do we know that when an ionic compounds are dissolved in water, that they are present as separate or dissociated component ions? Well, it's quite interesting and quite simple, really. What we find is that solutions of ionic substances are electrically conductive, or what we say is that they are electrolytes. And what that means is that there must be mobile charged particles present in aqueous solutions of ionic compounds. So when a solid crystalline ionic compound is dissolved in water, the product must be individual cations and individual anions that are moving around independently of each other. This is quite easy to determine in the lab. If we take a sample of distilled water, it is composed of electrically neutral water molecules, and unsurprisingly, it doesn't conduct. If we take a sample of solid sodium chloride, there are no mobile charged particles present because all of the cations and anions are locked in place in the solid crystalline lattice, and it also doesn't conduct. Now, if you combine the two and pour the water onto the salt and create an aqueous solution of sodium chloride, you will find that it conducts. And why does it conduct? Well, because we have sodium ions and chloride ions that are able to independently move. The sodium ions will move towards the negative electrode, chloride ions will be attracted towards our positive electrode, and this will result in conduction of an electric current. So we know that when an ionic compound is dissolved in water, what results is a solution containing individual mobile cations and anions. Some covalent compounds are also soluble in water, and a good example of this is ethanol. You probably know that alcoholic beverages contain ethanol. When we dissolve ethanol in water, it doesn't separate out into anions and cations, but rather just remains as intact molecules. And this is true for most covalent compounds. Most covalent compounds do not dissociate into ions, but remain as intact neutral molecules. And for that reason, the aqueous solutions formed by most covalent molecules do not conduct electricity, and they are described as being non-electrolytes. Some covalent compounds, what we call weak acids, are what we could describe as weak electrolytes. That is, they partially separate into ions when dissolved in water. And a good example of this is the weak acid, acetic acid, which is the acidic component in vinegar. When acetic acid is dissolved in water, a few percent of the molecules will dissociate into anions and hydrogen ions. In particular, the acetate anion. So as a result, what we will see is that solutions of these weak acids or these weak electrolytes will be mediocre, they'll be bad conductors of electricity, but they will conduct electricity to a certain extent. We will find that some ionic compounds dissolve well in water. In fact, many ionic compounds dissolve well in water. These ionic compounds are typically found in the ocean, and they are what contributes to the ocean being salty. Other ionic compounds have poor solubility in water, and they tend to not be found in the ocean, but rather to be found on the land. And a good examples of this would be things like carbonates, calcium carbonates, and phosphates that form like limestone and other rocky formations on land. Now, when do we consider something to be insoluble? For our purposes, if the maximum solubility that you can achieve is 0.01 mole per liter of that compound, then we're going to consider that compound to be insoluble. We aren't going to be discussing situations where things are described as being partially or poorly soluble. We're just going to have kind of a black and white cutoff of things being either insoluble or soluble. But of course, it's kind of a fuzzy boundary. One way of characterizing a solution is to describe it as being saturated. A saturated solution is one that contains the maximum amount of solute that is possible to dissolve in a given solvent. Typically, how we will know that a solution is saturated is when you add more solute, it just simply falls to the bottom. So that's a good way of checking. Add a little more solute. If it falls to the bottom, you know you have a saturated solution. If you don't have a saturated solution and your extra solute dissolves, then we describe the solution as being unsaturated. How we make a saturated solution normally is we'll just keep adding solute until we get a nice fat layer of the solute at the bottom, and then we filter off the liquid that's above, and that'll give us a saturated solution. Sometimes it's possible to create what we call a supersaturated solution. That is, we have a solution that contains more solute than you would predict based on its known solubility. It's important to recognize that a supersaturated solution is unstable, and as soon as you disturb it, you'll tend to get the extra solute crystallizing out. Normally, we'll form a saturated solution by forming the solution in a hot solvent and allowing it to cool very slowly, or alternatively, we'll take a saturated solution and we'll slowly evaporate a little bit of the solvent. So I'd just like to kind of show you a famous substance for which it's possible to form a supersaturated solution, and that is sodium acetate. And you can find recipes to do this at home if you're committed to seeing this yourself. So supersaturated sodium acetate, as soon as you disturb it, the excess solute will begin to crystallize out. And this is often described as hot ice because the crystallizing of the excess solute actually causes the temperature to go up. And here you can see it got up to above 52 degrees Celsius. So putting a finger or a meat thermometer in there causes the excess solute to precipitate out. Other disturbances can also cause it to precipitate out. For example, if you pour it and it hits a solid surface, that'll cause the excess sodium acetate to precipitate, and they're going to demonstrate to you that right now. So here you can see just the impact of the solution hitting the pan there causes the excess solute to precipitate out, and you can kind of create these stalactite type structures. It's kind of fun to play with. This stuff is often used in heat packs, the kind of heat pack that you have to heat up beforehand and then allow to cool slowly. And then when you disturb it by shaking it or pressing a little popper button inside, the excess solute comes out, And as mentioned previously, that crystallization process is exothermic and it generates heat. So you might have seen heat packs that contain supersaturated sodium acetate. Okay. So the way that we're going to identify whether an ionic compound is soluble or not is by using solubility rules. And so first we want to remember the solubility rules for ionic compounds that tend to be soluble. So ionic compounds containing the following ions tend to be soluble. Group 1A cations and the ammonium cation. If your compound contains those guys, it is always soluble with no exceptions. If your ionic compound contains the nitrate anion, it is always soluble without exceptions. If your ionic compound contains the acetate anion, it is always soluble without exception. If your ionic compound contains a halide or group 7A anion, it is normally soluble except for if the cation is either silver, lead 2+, copper 1+, or mercury 2+. If your ionic compound contains the sulfate anion, it is generally soluble unless it is accompanied by the calcium, strontium, barium, silver, or lead 2+ cation. Ionic compounds containing the following ions tend to be insoluble, and there are a lot more exceptions here. Hydroxides tend to be insoluble, except those containing group 1A or the calcium, strontium, or barium cations. Carbonates tend to be insoluble, except those containing group 1A or the ammonium cation. Phosphates tend to be insoluble, again, except those containing group 1A or the ammonium cation. Sulfides tend to be insoluble, except for those containing the group 1A, ammonium, or calcium, strontium, or barium cations. So that's really the list. Those rules will do you really well. They're a little tricky to memorize, especially all of the exceptions. There are a couple of tools that can help us when we first start working with solubility rules. One of them is a solubility rules chart like this one, where you have anions on one axis and cations on another. And if we want to find whether a compound is soluble or not, we kind of do the grid reference sort of thing. So say, for example, we're trying to establish whether magnesium sulfate is soluble. We would have to find magnesium on the appropriate axis and sulfate on the appropriate axis. And then we would draw across, do the grid reference thing, and we would find that magnesium sulfate is soluble, and so we know that it can form an aqueous solution. So that's one tool. These are kind of limited in their scope. They don't cover all your bases. You can see there's not very many metals there, just a few metals there. There are many more metal ions on the periodic table. We also don't have very many cations either. So these are helpful, but not complete. The other thing is people propose memory aids or memory tricks to help you remember the solubility rules. This is kind of like the one that works kind of the best for me. Always soluble, we've got NAG, SAG. So this is nitrates, acetates, group 1 for the NAG, and then sulfates, ammonium, group 17 for the SAG. There are exceptions, of course, and people will try to remember this using the memory aid PMS Castro Bear. this doesn't work so well for me. The P represents lead 2+, the M is mercury 2+, the S is silver. The Castro bear is meant to represent calcium, strontium, and barium. So I find these kind of little memory tricks not that helpful. What I find helpful is just doing a bunch of problems and eventually you memorize it slowly by looking at the table. Okay, so one of the ways that we're going to use these tools is when we're looking at reactions where two solutions of ionic compounds are combined, and we're asked to predict if a precipitate forms. So this is actually a reaction that we often do in the lab. Aqueous strontium chloride is combined with aqueous sodium carbonate, and it forms a solid or precipitate of strontium carbonate and an aqueous solution of sodium chloride. So how could we predict this result? So we have two solutions that we're combining. Solution 1 is a strontium chloride solution, and solution 2 is a sodium carbonate solution. We know that in an aqueous solution of an ionic compound, it will dissociate to form its component ions. So the strontium chloride will dissociate to form strontium 2+ aqueous solution and a chloride Cl- aqueous solution. The sodium carbonate will dissociate to form sodium ions and carbonate ions in aqueous solution. Now, if we mix these two solutions together, we will have all 4 ions present in the one solution. So how can we predict that if a precipitate will form when these solutions are combined? Well, what we have to do is consider the new pairs of ions that can form because these guys have been combined. So in particular, we have to compare what happens when strontium ions combine with carbonate ions and what's going to happen when sodium ions combine with chloride ions. So we're going to go look at our solubility rules and do just that. And when we do this, what we recognize is that sodium, when it's combined with chloride, doesn't form a precipitate because sodium chloride is soluble. But when strontium ions are combined with carbonate ions, the resultant product, strontium carbonate, is insoluble, so solid strontium carbonate will form when these two solutions are combined. So we can express this using what we call the molecular equation, where all compounds are written in their undissociated forms. So strontium chloride is combined with sodium carbonate, and that results in the formation of sodium chloride, which is present as an aqueous solution, and strontium carbonate, which precipitates out of the solution. Now, this is helpful. We have to be really careful to pay attention to the phase labels in order to understand that a solid is formed. A more realistic way and a more helpful way of writing what is going on here would be to write those species that dissociate as their individual ions. So rather than writing strontium chloride AQ, because the ionic compound dissociates when it's dissolved in water, we can write this as the individual ions. Similarly, rather than writing sodium carbonate AQ, we're going to dissociate this into the component ions that are actually present in the aqueous solution. Strontium carbonate is a solid, so that it's not present as dissociated ions, so we're not going to dissociate this in any way. But sodium chloride AQ will separate out into its component ions. And so again, we're going to write that to make it clear as the component ions. So when we write the equation in this way, where we've dissociated completely all of the compounds that are present as individual ions, we get the overall, or sometimes people call it the total ionic equation. And so that makes it clear what's happening. We create a mixture of 4 ions, 2 cations, and 2 types of anions. Strontium ions combine with carbonate ions to make solid strontium carbonate, and the remaining ions stay in solution as the individual ions. One thing that we can do is we can eliminate or cancel what we call spectator ions. These are ions that appear in the same form on both sides of our arrow. So you can see here that the sodium ions and the chloride ions are in exactly the same form on both sides of the arrow. That means that they don't in any way react. So we can go ahead and cancel these spectators to give a clearer view of what's going on. And when we do that, we end up with what's called the net ionic equation, which is strontium ions combined with carbonate ions to form solid strontium carbonate. And they're going to do this in a 1-to-1 ratio because they have equal and opposite charges. So you do want to be a little bit careful when you're asked to write the equation for a precipitation reaction. You want to make sure that you know whether you're being asked for the molecular, the overall ionic, or the net ionic equation, and to give the appropriate version of the equation. So here's a classic question. It says, predict if a precipitation reaction occurs when solutions of silver nitrate and iron 3 chloride are combined. If a reaction occurs, write the net ionic equation. So our first solution is aqueous silver nitrate, and that's going to dissociate to give aqueous silver ions and aqueous nitrate ions. Our second solution is aqueous iron 3 chloride, and that's going to dissociate to give aqueous iron 3 plus ions and aqueous chloride ions. So now we need to think about what's happening in our mixture. Well, we have 4 ions present, and we have some possibilities for new interactions that weren't possible in the individual solutions. In particular, the Fe3 plus ions can now interact with the nitrate ions. And if we remember our solubility rules, anything containing the nitrate anion, without exception, is soluble. So when iron 3 plus ions encounter a nitrate ion, they will not form a precipitate. However, when we check what happens when a silver ion encounters a chloride ion, we see that silver chloride, according to our rules, is insoluble. So what that tells us is that a precipitate will form between silver ions and chloride ions. So what would be the formula of that precipitate? Well, silver ions and chloride ions have equal and opposite charges, so they're going to combine together to form solid, we don't need 2 of those, solid silver chloride. So we've kind of answered the first part of the question. Yes, a precipitation reaction will occur, and the product of that reaction will be solid silver chloride. So now we need to work our way towards the net ionic equation. So we've got to the point where we've predicted that solid silver chloride will form. Let's now work up the equation. So what we have to think about is we want to dissociate everything into the component ions. We want to cancel spectator ions, and we also want to generate a balanced equation, because we can see when we write this molecular form of the equation that it's not going to be balanced, right? That it isn't currently balanced. So we've got the correct products here. We identified previously that the silver will combine with the chloride ions to form solid silver chloride. We had to do a little bit of work here with the crossover rule. We identified that the iron 3 will react with the nitrate anions to form a soluble solution. The ionic compound that will form will have a 1:3 ratio of iron 3 plus ions to nitrate ions, because these guys have different charges, and we're just going to get that ratio using the crossover rule. Okay. So now we kind of have to bring it into balance. And I hope that what you see is that we're going to need 3 silver nitrates to give us the 3 nitrates, and we're going to need 3 silver chlorides because we need our chlorides and our silvers to also balance. Okay, so now we've got this equation. What we can do is we can set about separating this guy out into the component ions. So, having done that, it looks kind of like this, right? The 3 silver nitrate AQ is going to separate into 3 silver ions and 3 nitrate ions. The 1 Fe or iron 3 chloride solution will separate out into iron 3 plus ions and 3 chloride ions. The 3 silver chlorides, because it's solid, they will not dissociate. And then the iron 3 nitrate will separate out into iron 3 plus ions and 3 nitrate ions. So that's the first step. That gives us the overall ionic equation. What we're now going to do is cancel our spectators. So we're looking for ions that appear in the same form on both sides of the arrow. And you can see that's going to be our nitrate and our iron 3 plus ions. So we'll go ahead and get rid of those guys. And that gets us pretty close to our net ionic equation. So at this point, it would look like this. And I hope what you can see is we're not quite done, because we can divide through by the common factor of 3. And when we do that, that'll give us our overall properly balanced net ionic equation. Now, I'm going to kind of show you the shortcut right now. In our first step, we identified that silver chloride solid would be our precipitate. And one way of getting the net ionic equation for a precipitation reaction is just to dissociate what you know to be the product. So in this case, we would dissociate silver chloride into its component ions. And there you can see is a short way of getting the net ionic equation in a single step. Something that you've you probably recognize in that problem is we combined the precipitation reaction with naming. You had to know how to turn the names silver nitrate and iron 3 chloride into formulas. And that's not uncommon at the general chemistry level. It makes the question a lot more challenging. It does happen at the general chemistry level. The other thing we might do is introduce concepts of stoichiometry, that is, calculations involving the amounts of things. So a classic example would be something like this. It says determine the mass, there's the stoichiometry bit, of precipitate that forms when 25 milliliters of a 0.1 mole per liter solution of silver nitrate is combined with excess iron 3 chloride. So excess just means that you have more than what could ever possibly react. So this is kind of a challenging problem. The first thing that we're going to want to do is we're going to want to, well, make sure that we have enough space to answer it. So always give yourself plenty of space to answer these questions, and I've modeled that here by starting a new slide. Before you can begin doing a stoichiometry calculation, you always want to get a balanced chemical reaction. So let's think about what we're reacting here. We're reacting silver nitrate with iron 3 chloride. So our first solution is going to be silver nitrate. So silver is a +1 charge and nitrate is a -1. Okay, so silver nitrate. So these guys are going to combine together in a 1-to-1 ratio to form an ionic compound, and we're starting with an aqueous solution of that, and when it dissociates, it's going to form our silver ions and our nitrate anion. Okay. Our next solution is iron 3 chloride. Well, the charge on the iron is going to be Fe3+, that's indicated by the Roman numerals. And then chloride ions, well, chlorine's in group 7A, so that's going to be a -1 ion. So we'll have to use crossover this time to get the ionic compound that they form. So that's going to be FeCl3. So the two solutions are going to be AgNO3AQ and FeCl3AQ, which of course will dissociate to form Fe3+ and chloride anions. So now we have to think about the new combinations that can form. Remember our solubility rule, nitrates are always soluble, so iron 3+ and nitrate are not going to form a solid, they're going to form an aqueous solution. However, as we saw previously, when silver ions are combined with chloride ions, they do form a solid. So we know that we're going to form AgCl solid. And how do we know that there's one of each ion? Well, Ag+ chloride ions have equal and opposite charges. Okay. Let's just create a little space here. Okay. So now what about our other product? Well, that's going to be iron 3 nitrate. And again, we have to use crossover to get their ratio there because they don't have equal and opposite charges. So we need 3 nitrates to balance out the charge on the iron. And that's going to form an aqueous solution, isn't it? Okay. So there are our products. And then the two things that we're combining are silver nitrate AQ and FeCl3AQ. Okay, so now we've got to get it to balance. So to get the chlorines into balance, we're going to need 3 of those. And then to get the silver and the nitrates to balance, we're going to need 3 of those. So there's our our molecular form of the equation, which is perfect for doing our math. So I'm going to make some more space again. Now we can do our mathematics. So we're starting with 25 mils of our silver nitrate, and we have to think about how many grams, because it's asking for mass, of our product that we need. Ooh, got a little weird there, didn't it? How many grams of our product, which is our silver chloride that we're going to produce. So let's see what we've got here, right? So we've got 25 mils of aqueous silver nitrate, and according to the problem, we get 0.1 mole of silver nitrate for every 1 liter, or another way of saying that is for every 1,000 milliliters, right? Because there's 1,000 milliliters in a liter. Now, because we've got a balanced equation, we know we get 3 moles of silver chloride, our solid, for every 3 moles of silver nitrate. So at that point, what do we have? Well, we took our milliliters and we turned it into moles of silver nitrate with our first conversion factor. And then using our mole ratio, we turned the moles of silver nitrate into the moles of silver chloride. So there's only one thing left to do. We need to take moles of silver chloride and we need to turn it into grams of silver chloride. And hopefully you remember how we do that is by multiplying by the molar mass. So the molar mass of silver chloride is 143.32 grams for every 1 mole. And there we are, we're done. So now we just put that into our calculator. I'll just pop that up. It's going to be weird. Here we go. Turn it on. 25 times 0.1 on 1,000 times, you don't really need to do the 3 on 3, but we can just do it for completeness, times 143.32. There we go. And so there's our answer. We began with 2 sig figs, so this is going to be 0.36 grams. So let's look at a problem from the OpenStax book. This one reads, the mineral fluoride, which is calcium fluoride, occurs extensively in Illinois. Solid calcium fluoride can also be prepared by the reaction of aqueous solutions of calcium chloride and sodium fluoride, yielding aqueous sodium chloride as the other product. Write complete and net ionic equations for this reaction. So we're making calcium fluoride. So let's think about the formula of that. Calcium's in group 2A, fluorine's in group 7A. So from the group positions, we can get the charges. We see that they're not equal and opposite, so we're going to need to do crossover in order to get the formula of calcium fluoride. So it's going to be CaF2, and that's a solid, and that's going to be our product. So getting the net ionic equation, if you remember, there's a little shortcut that we can do. We can take our product and we can simply separate it into its component ions, and that gives us the net ionic equation. So 50% of the problem was relatively easy to do. Okay, the next part is like a little bit more complicated. We have to figure out the formula of calcium chloride, sodium fluoride, and sodium chloride. So calcium chloride, calcium's still in group 2A, so it's still 2+. Chloride is also in group 7A alongside fluorine, so these guys are going to combine in a 1:2 ratio as well. Sodium fluoride is a little easier. Sodium's in group 1A, so it has a 1+ charge. Fluorine still has a 1- charge. The sodium fluoride is just going to have the ions combining 1:1. And similarly with sodium chloride, sodium is in group 1A still, chlorine's still in group 7A, so those guys are going to combine 1:1. So let's put it all together. Calcium chloride aqueous combines with sodium fluoride aqueous to form calcium fluoride solid and sodium chloride AQ. And we're going to have to do a little bit of adjustment here to get everything to balance. Okay, so there's our molecular form of the equation with the correct phase labels. To get the complete ionic equation, we have to separate all of the ions out where possible. So anything that is AQ is going to get dissociated into component ions. So in this case, that's anything other than the calcium fluoride. And this tends to get pretty long. And you can see here, I'm actually going to kind of run out of space, keeping it all on the one line. And it's one of the reasons why we prefer the net ionic equation, because it kind of just focuses your attention on what needs to be, what you need to understand is going on. So there's the net ionic equation. And then this guy here is the complete, or sometimes people call it the total ionic equation. And we can check our answer against what OpenStax has. And sure enough, we got it correct. Okay, well, I hope you found that helpful. It'll take a little time to master this content, but this is part 1 of section 4.2, classifying chemical reactions.